So to get good statistics on amino acid substitution probability, you have to compare a lot of sequences, like thousands is what we're talking about. Okay, so just looking at a few wouldn't be enough to get you any statistical power to trust your results. Okay, you also don't want sequences that are too similar. Okay, you need enough time and enough divergence in evolution to actually make anything of the substitutions you're finding. If you were to use stuff that's too similar, it would skew the results. And remember that percent identity is related to evolutionary time. So to sort of fix this, we set some sort of cutoff of sequence identity, and the most common choice is 62. So only sequences that are 62% identical or less are included in the comparisons. And so the matrix in our textbook is a BLOSSOM 62 matrix. It's the one we'll use. But if you wanted to make a matrix, you can make BLOSSOM 75. You can make BLOSSOM 90. That just means the stuff is more closely related. We kept in sequences that were really, really similar. You could go even lower. You make a BLOSSOM 40 matrix, whatever it might be. And the first video link on the first page of this slide is one that talks a little bit about choosing it. And like I said, it goes through all the stats of building the matrix from scratch, if that's of interest to you. I do find it very cool, but I don't have time to teach you. Okay? So BLOSSOM 62 is the one we're looking at. Okay, it's a very common example of a protein scoring matrix. It was derived from a very large block of aligned protein sequences. Like I said, you need at least 1,000. So entries in the matrix are called substitution scores, or Sij. They relate the frequency with which the ith type amino acid is replaced by the jth type, or vice versa. They're the same either direction. And we talked a little bit how to interpret the scores. A positive score is something that actually happens more frequently through time than random chance. 0 represents it's the same likelihood that those two would swap, it's just totally randomly. And negative scores mean it's less likely to occur. And I think this is just the exact same sort of scoring details as before. So substitution scores, our Sij, are determined from the substitution likelihood ratio, or Lij. Okay? The derivation of these equations and matrix construction is, there's details in your textbook, box 5.2, pages 203 to 207. I don't need you to use any of those equations unless you want to. Here's the only one you need, and it will be given. Okay? So this is the relationship between the likelihood ratio and the substitution score. Sij is what's actually in that matrix, and it's related to a likelihood of substitution constructed here. So it is the frequency of the Ij substitution in the alignment block of related proteins over the frequency of that substitution if everything was totally randomly scrambled. Okay? And so that's why I said, and I think actually this pops up. So what does it mean if L is 1? If L is 1, what is the log in base 2 of 1? It's 0. So times 2 doesn't mean anything. The substitution score is 0. Okay? And we said when substitution score is 0, L would be 1. It means that the frequency of finding that substitution in your aligned block over the frequency of finding that substitution if you randomly scrambled all the amino acids in that block is the same. Okay? It's a 1-to-1. It's random chance. If L is greater than 1, what kind of score are we going to get? We're going to have a positive score. We're going to get something more likely to happen. When we have a number less than 1, the log of a number less than 1 is a negative number. We're going to get a negative score for Sij. Okay. Like I said, if the first, actually, they talk about a little in both of the two BLOSSOM videos, the first 2 links that I posted, talk about all of these equations. Again, I will only ask you to use this one. But I would like you to understand qualitatively and mathematically the relationship between the score that you're getting in the matrix and the likelihood of that substitution. Okay.